Welcome to Global Watch. Please subscribe and hit the bell icon for more breaking updates. In a cryogenically cooled chamber nestled in the heart of Santa Barbara, California, a place where the air shimmers with cold and the hum of technology is ever present, something extraordinary has happened here. In a facility that looks more like a set from a science fiction film than a real-world laboratory, the boundaries of human knowledge are pushed every day. This is the home of one of the world's most advanced quantum computers, a machine designed not just to compute, but to explore the very fabric of reality itself. But now, Google's Willow quantum computer has fallen silent. The once busy hum of processors and the blinking lights of activity have faded, replaced by an eerie stillness that hangs heavy in the air. Just weeks before, Willow performed a calculation so complex, so unprecedented, that it reignited one of science's oldest and most profound debates. Are we truly alone in the universe, or are we just one thread in a vast tapestry of infinite realities? The results were so astonishing that they sent ripples through the scientific world, sparking late-night debates and wild speculation about the nature of existence itself. The sudden, unexplained shutdown of Willow has sent shockwaves through the scientific community. Researchers who once gathered eagerly around screens now stand in stunned silence, their excitement replaced by concern and confusion. News of the event has spread rapidly, dominating headlines and prompting urgent meetings among the world's leading physicists. Quantum computers aren't just faster versions of the machines we use every day. They harness the bizarre, counterintuitive rules of quantum mechanics, allowing them to solve problems that would take classical computers millions of years. They operate in a realm where particles can be in two places at once, and where information seems to leap across space and time. Now the silence from Google's lab is more than just the absence of sound. It's a deafening pause in our journey toward a future shaped by quantum discovery. The empty halls and darkened screens are a stark reminder of how fragile progress can be. As engineers and scientists scramble for answers, poring over data and running diagnostics late into the night, the world waits with bated breath. Some wonder if Willow glimpsed something it shouldn't have, if, in its quest for knowledge, it crossed a line that was never meant to be crossed. The story of Willow is no longer just about a machine or a calculation. It's about the boundaries of knowledge itself, and the mysteries that await us when we dare to cross them. Quantum computing's roots lie in the early 20th century, when physicists like Einstein and Schrödinger uncovered the strange world of superposition and entanglement. These groundbreaking discoveries challenged our understanding of reality itself, revealing that particles could exist in multiple states simultaneously and be instantaneously connected across vast distances. This was a radical departure from classical physics, which had dominated scientific thought for centuries. For decades, these effects were scientific curiosities, not tools for computation. Scientists marveled at the bizarre behavior of quantum particles, but practical applications seemed out of reach. Theoretical physicists continued to explore these phenomena, laying the groundwork for future breakthroughs. In the 1980s, Richard Feynman and David Deutsch imagined harnessing quantum rules for computing, leading to the concept of the qubit. They proposed that quantum mechanics could revolutionize computation, allowing for the processing of information in ways that classical computers could never achieve. This was the birth of quantum computing as a field of study. Unlike classical bits, qubits can be 0, 1, or both at once, enabling exponential computational power. This unique property, known as superposition, allows quantum computers to perform many calculations simultaneously, vastly increasing their potential speed and efficiency. But qubits are fragile. Environmental noise can destroy their delicate state in an instant. This sensitivity to external disturbances, known as decoherence, poses a significant challenge to the development of reliable quantum computers. Building a quantum computer became a quest to protect qubits long enough to perform useful calculations. Researchers developed sophisticated techniques to isolate qubits from their environment, using advanced materials and cryogenic temperatures to maintain their quantum states. The challenge was immense, not just creating qubits, but shielding them from the chaos of the outside world. This required innovative engineering solutions and a deep understanding of quantum mechanics. This pursuit would define quantum research for decades. The journey from theoretical curiosity to practical technology has been long and arduous, but each step brings us closer to unlocking the full potential of quantum computing. Google's Quantum AI Lab, founded in 2012, set out to make quantum computing practical. Their 2019 Sycamore processor achieved quantum supremacy, solving a problem in 200 seconds that would take classical supercomputers millennia. But Sycamore's qubits were still error-prone, limiting real-world applications. Enter Willow, a 105-qubit processor announced in 2024, designed for robust quantum error correction. Willow's qubits had much longer coherence times, making them more stable and reliable. For the first time, complex error correction codes could be implemented in real time. Willow wasn't just bigger, it was a prototype for a truly scalable, fault-tolerant quantum computer. The field's holy grail was finally within reach. The greatest obstacle in quantum computing is error. Qubits are like spinning coins. Any disturbance collapses them, introducing errors. Quantum error correction encodes a logical qubit across many physical qubits, constantly monitoring for errors without destroying the quantum state. For years, error correction introduced more problems than it solved. The breakthrough came when Willow's error correction code actually improved performance as more qubits were added. In 2024, Google demonstrated that logical qubits became exponentially more stable as they scaled up. This proved that large-scale, fault-tolerant quantum computing was now an engineering challenge, not just a theoretical dream. Willow provided the blueprint. With error correction mastered, Willow tackled random circuit sampling, a problem classical computers can't touch. Willow completed the calculation in under 5 minutes. A classical supercomputer would need 10 septillion years. This was a quantum leap, not just an incremental advance. Willow's logical qubits unlocked a new computational realm, silencing doubts about quantum supremacy. The technical achievement was celebrated worldwide, but controversy erupted when Hartmut Neven, Google's quantum lead, claimed Willow's power hinted at the existence of parallel universes. He suggested that only the multiverse could explain such vast computational speed. The calculation was done, but the debate was just beginning. Had Willow touched the multiverse? The many-worlds interpretation proposed by Hugh Everett suggests every quantum event splits reality into parallel universes. Hartmut Neven argued Willow's speed lent credence to this idea. Quantum computation might occur across countless universes. Supporters saw Willow's achievement as indirect evidence. How else could a small chip explore such vast computational space? Critics countered that this was philosophy, not science. Quantum mechanics works without invoking a multiverse. Other interpretations like Copenhagen explain quantum phenomena without parallel worlds. The multiverse remains a tantalizing, but untestable, hypothesis. Willow's calculation reignited the debate, but offered no definitive proof. For now, the multiverse is a story we tell to make sense of quantum strangeness. The multiverse debate split the scientific community, igniting passionate arguments in lecture halls, research labs, and online forums alike. For some, the idea of countless parallel universes was exhilarating, a bold new frontier that could redefine our understanding of reality itself. Some saw Google's claim as a daring insight, a glimpse into the hidden structure of the cosmos. Others, however, dismissed it as a leap into metaphysics, arguing that extraordinary claims demand extraordinary evidence. The room was divided, with excitement and skepticism in equal measure. Critics like astrophysicist Ethan Siegel were quick to point out that quantum mechanics, as strange as it is, doesn't require the existence of parallel universes. The mathematics, they argued, works perfectly well without invoking other worlds. For them, the multiverse was an unnecessary complication, an idea that, while fascinating, lacked direct evidence. On the other side, proponents like David Deutsch, a pioneer in quantum theory, insisted that the multiverse offers the most compelling explanation for quantum phenomena. They pointed to experiments like the double-slit interference pattern, where particles seem to behave as if influenced by invisible counterparts, as tantalizing hints that parallel realities might be more than just science fiction. Yet, despite the passionate arguments, most scientists remain agnostic. They acknowledge the allure of the multiverse and the elegance of its mathematics, but they also stress the importance of testable proof. Without concrete evidence, the multiverse remains a hypothesis, an intriguing possibility, but not yet a scientific fact. Dr. Anya Sharma of Oxford summed it up best: Willow's achievement is a triumph of engineering, pushing the boundaries of what quantum computers can do. But when it comes to the multiverse, she cautions, we are still in the realm of speculation. The evidence, she says, simply isn't there, at least not yet. What is certain is that Willow's calculation was astonishingly fast, a feat that no classical computer could match. But the deeper meaning of that speed, whether it hints at hidden universes or simply reflects the quirks of quantum mechanics, remains hotly debated. For now, science can't say if Willow's qubits truly danced across parallel worlds, or if their power comes from something else entirely. The mystery endures, fueling both skepticism and wonder. The search for answers continues, as scientists push the limits of knowledge, hoping one day to unlock the secrets of the quantum realm, and perhaps, the multiverse itself. Beyond the multiverse debate, Willow's success marks the dawn of a new technological era. Robust quantum error correction unlocks applications that could transform medicine, materials science and energy. Quantum computers will simulate molecules, design drugs, and create new materials with unprecedented precision. They'll revolutionize logistics, finance, and even artificial intelligence. But this power also threatens current encryption, demanding new quantum-resistant security. Quantum computing is set to accelerate scientific discovery and reshape industries. Willow is more than a faster computer, it's the engine of a new age. Willow's mysterious shutdown is a symbol of our moment, on the edge of a quantum revolution, but facing unknowns. The world awaits Google's explanation. Was it a hardware glitch, or something deeper? The real race now is for high-quality logical qubits with low error rates, not just more qubits. Competitors like IBM and Microsoft are pushing the frontier too. We must also consider the ethical, economic, and security implications of quantum technology. Preparing for a post-quantum world means investing in education and new safeguards. The story of Willow is a wake-up call. We all have a stake in this revolution. The future isn't just to be predicted, it's to be built.